Currently, he also serves as a strategic advisor to Citigroup. At IBM, among things that he did for many years, he was responsible for identifying emerging technologies and marketplace developments. He was the chairman of the Board of Governors of the IBM Academy of Technology and a leader of a number of projects at IBM, including the Internet Strategy, Linux and grid computing, and on-demand business. In his spare time, he's been involved with a lot of other activities, including higher education. He was and is, I think, associated with MIT, both in the School of Engineering and the Systems Engineering Division, which I think will be of interest to a number of people here in this room, and also in the Sloan School of Management, where he's been a visiting lecturer. At the State University of New York, he's a senior fellow at the Levin Institute. At Imperial College in London, he's an adjunct professor of innovation and entrepreneurship. And his interest here is how technology can transform business organizations and the institutions of society. So this is very much at the heart of a conversation that Olin is very interested in, and that is extending engineering systems thinking to problems that involve social and economic context. He's also involved at British Petroleum as a technology advisor on their council. At the University of Chicago, where he's also an alum and has his MS and PhD. He's on the visiting committee for physical sciences. At the University of Texas at Austin, he's on the board of visitors for the Institute of Computational Engineering and Science. And he's also had roles at the National Research Council and computer science and telecommunications and a number of other areas there. He's been involved with Argonne National Laboratory and Fermilab on their various boards of governance and boards of visitors. He's a fellow of the AAAS. Interesting, when you hear him talk, you will notice that he has come from a different part of the world. And with a name like Wladawsky-Berger, I had really expected to find somebody from maybe Eastern Europe. Turns out he was born in Cuba and recently came to America at age 15, and in 2001 was elected the Hispanic Engineer of the Year. So I think we're just absolutely delighted to welcome you here today to talk about building a smarter planet, linking the physical and the digital worlds. Irving.
It's always a pleasure to come to Olin College. I have to say, the first time I came here, when some of my IBM colleagues, Carla Good, said you have to be there, you have to come, or Doug Hunt, I was so happily surprised to see what Olin is all about and what the president, President Miller was writing about, because it so matched my views about the future of where engineering, technology, and science need to go. And what I'd like to talk about this morning is a very concrete application of that future. Now let me ask you, treat this less as a talk than a seminar, and by that it means at any point, if you have any question or comment, ask me, and you get extra points the more controversial it is. So if you agree with me, it's good, but if you don't agree with me, it's much better. So feel free not to agree. So what I'd like to talk then is, where is this all heading? And in particular, I think there are some massive historical changes taking place in where we are applying science and technology. And maybe to put this in the proper context, let me start by reminding you of other times when we have had massive historical changes in the application of science and technology. And let's see, if we go back and start looking at what we now call the Industrial Revolution, which came up roughly toward the end of the 18th century, what the Industrial Revolution was all about is the application of science and technology. There was no engineering yet, that came later, to the physical world around us. And what people did is lots of things that before the Industrial Revolution were done purely by hand, whether it was weaving things or making nails or whatever, were done totally by hand. You wanted, I don't know, 500 nails, you went to your blacksmith, and he, or I could say he or she, I suspect there were very few female blacksmiths in 1780 in London. And if there were some, we probably have novels about her. She must have been quite a gal. But that was all done by hand, and through new technologies, new tools, new knowledge, and through the application of science and technology, we learn how to design it and manufacture it far, far better than ever before. And in fact, we then started to say, well, why don't we sort of capture all that learning about how you do these things and invent a new field. And of course, the new field was engineering, which roughly, I think it started in the 1850s, 1860s. The second half of the 19th century is when engineering started. Before, there was no Industrial Revolution. It was all sort of natural science and philosophy. And by now, as we know, engineering, technology, and science have made incredible progress and given us all kinds of ways to design and manufacture the most incredibly complex physical things imaginable, from Airbus 380s, 787s, all kinds of automobiles, microprocessors with billions of transistors, on and on and on and on, all stuff you all know. Now, about 40, 50 years ago, we got our own new version of steam power, which is the world of digital technologies and digital components. And as we know, that has been making tremendous progress over the years. And if I had to put sort of a date when this whole digital component stuff really started to change the world in a huge way, I think it's when the internet and the web first appeared in the wider world in the mid-90s. And the reason for that is that when something that changes the world happens, one of the indicators is nobody can remember what the world was like before. You just can't remember. I mean, I know many of you were small children then, but I wonder if any of you students, not faculty, can remember when there was no web. Are there any of you here who remember a time when, I don't know, if you wanted to know tomorrow morning, in case you care, here in the Boston area, who won the first game of the World Series, you had to, I don't know, turn on the television and wait till they wanted to tell you, or turn on the radio instead of going to the web. Anybody remembers that world? You remember that? Doesn't it feel primitive? It's as if I told you that there was a time we had no cars and, horse buggies, whatever. the changes have been so profound and so integrated into our personal lives that it clearly started taking us in an absolutely different direction. And it has been systematically changing the world. So, what kind of world are we living in today? Well, if any of you have read The World is Flat, I'm assuming you all are familiar with Tom Friedman's book, even if you didn't read it. What makes that book so compelling is Tom capturing it's a very good metaphor for how the internet and technologies have sort of integrated the world and made it all so much closer than anything that was ever there before. And what it has done is all of a sudden the world itself and all these things around it, we can start looking, or not we can start looking, we need to start looking at systems, but because these things are so complicated, they're not just systems. They are systems of systems. And they are systems of systems in which the components are changing very rapidly. And if anybody here studies system dynamics and stuff like that, when you have a highly integrated system with fast-changing components, that system is totally unpredictable, but totally unpredictable. I mean, just, it's NP complete. It's as unpredictable. Or somebody said, no, Irving, you don't understand. We have this very smart person, but it's as if somebody said we have this very smart person that can do, I don't know, chips where things go faster than the speed of light. I said, well, that's cool, but I don't think you can do that. And it's that degree of unpredictability. By the way, if you want to know how new this all is, remember that Nobel Prize economists had no idea that the world had become unpredictable just a year ago. They were as surprised as anybody else to realize, oh my God, the world has changed since I got my Nobel Prize. And I didn't notice that I'm being very serious. And these are smart people, just that they didn't realize that what they learned 20, 30 years ago was no longer the world we live in today. And they totally missed this revolution that's been happening under them. But what I find the most fascinating part of these changes, and this is what I want to focus on, is that for the first time, we can study systems as systems. And when I say we can study systems as systems, what I really mean is we can apply engineering, kind of discipline, science and technology, where the components are not screws and wings and physical things that are nicely behaved. And when a screw will remain a screw and it will do what you tell it to do. But now we can do that with systems of people and the services they perform for each other. And contrary to what quite a few of these economists that sort of were caught by surprise, people are not deterministic. People are not, quote unquote, rational by the definition of the economists. Obviously, they're rational by what goes on in their mind, but who the hell knows what goes on in all of our minds, and it's all different. And all of a sudden, those are the systems that we can begin to apply engineering thinking and engineering discipline to. And in fact, I am convinced that the sort of big historical challenge ahead of us is how can we take all this wonderful science, technology, math, engineering that has served us so infinitely well in the industrial age applied to the physical world, but now apply it to this organizational world with people and components and the way the planet works. That, you know, it's just a great challenge ahead of us. And one, by the way, that for Olin, you could say, well, that's what you've been doing ever since you started, is figure out how to step up to that challenge. Now, every time that you say, well, we can do some new things, underneath that there has to be some new technology, some new capabilities that are let us do these new things. It's not enough to say, well, we're just smarter. That's true. But let's explore briefly what are some of the new things that are enabling us to now start looking at a world as a system, and especially at a world of organizational systems with people as components in this more systematic way. First of all, we have tons and tons and more tons of information. This is very important because, you know, if you look at what science engineering and all about is figuring out what the hell is going on. How do you figure out what's going on? You do experiments, you measure things. You need real-world information to figure out what's going on. And the more information you get, the more, if you do it right, you can better figure out what's going on. And I don't need to tell you that we have lots of information, much of it in real time. A second major, huge thing that is going on now is we are putting computers, and by a computer I mean something with a microprocessor, an operating system, software that you can program, and an IP address. That's a fair definition of a computer, right? And you can put it anywhere, and the damn thing is dirt cheap, as it should be because of the commoditization of all these digital components. And, you know, it wasn't that long ago, and this you all will remember, when by a computer you meant, oh, you mean a laptop? The answer is, well, yeah, I mean a laptop, but a laptop today is as much of a legacy as a mainframe. Now, being a legacy is not bad. IBM makes huge amounts of money from mainframes. But if I told you here that the mainframe is the center of research and innovation, you don't look at me funny because that it hasn't been for 20 years. Neither is the PC. Laptops are great. Microsoft will continue to make huge amounts of money. Apple, because of their emphasis on design, we'll talk more about that, is making even more profit, obviously not more money. But, you know, Microsoft is now in the legacy business, making lots of money from old stuff. I don't need to tell you, the center of action in computing is in mobile devices. And it is in the hundreds of billions, going to trillions of smart sensors that we are embedding in everything. Now, if you're going to have billions of mobile devices and trillions of sensors, you better have some really sophisticated, gigantic systems from which to manage all that. Well, have you all heard of cloud computing? That's cloud. That's sort of my view of cloud computing. It's what you need to build to be able to take care of all these things. And then it's all connected. It's all IP connected. We have more broadband. We have more wireless. So all this stuff is connected. And remember, most of what I'm talking about here, at the scale I'm talking about here, is really only recently here. I mean, we've been talking about it for a while. We've been talking about broadband and so on. You know, the more universal broadband and wireless and so on, we're not even totally there yet. So we do have these new tools that we can now use to do some incredibly new things. Please. Because, and I will talk more about it, but cloud computing, in my mind, is the industrialization of the data center, giving you the ability to build gigantic data centers that are very, very efficient, highly scalable, which is what you need to do these things. Because if you don't do that way, most data centers today were built for applications of much lower scale. And they couldn't possibly scale to what we need to do. If you look at the data centers of Google or Amazon or Yahoo, and a lot of what IBM does, those were much more engineered to be able to do things in a totally different way. So that's my view of cloud computing. It's not a universal view. I mean, different people have different views. But my main view is applying tremendous engineering discipline to what are essentially services and information factories. You know, look at what Toyota did in manufacturing 30, 40 years ago, the whole Toyota production system. Cloud is doing that to the equivalent of manufacturing in the world of information technologies, which are the data centers. Is that clear?
Clear. Yeah, that actually varies from the definition of cloud. Work with others, but based on how you define that.
Yeah, since, remember, there's no pope of cloud, so we all get to define it any way we like. And but notice that the kinds of things we associate. Let me ask you a question. What definition of cloud would you say? No, but it has to be highly scalable. Do you agree with me?
Okay.
And it has to be highly efficient from an energy system management cost. So, I mean, in my mind, cloud is a new computing model. And a model, as opposed to a thing, it's not just one thing. So different people can look at the elephant from their point of view. And the fact that cloud implies to the users of the cloud totally virtualized access to the services, it's absolutely part of cloud. But what happens when you make it really easy for people to access services is they will access tons of new ones, orders of magnitude more. And if you are not ready in the factory floor to handle that, you're dead. So I was emphasizing sort of the more hardcore engineering aspect of cloud, which is the factory floor. By the way, if you look at Google, some people say, oh, Google is so cute, they do all this great stuff. They run their data centers with Prussian precision. I mean, they are so disciplined just like Toyota. If I told you Toyota runs their factory floors with incredible discipline, nobody will be surprised. If you don't, then bad things happen to you. That's true in data centers also, except most people running data centers don't know that yet. No, I'm serious. I mean, things take a while to move on. So what do we do with all that stuff? Well, let me start by just reminding you that we are putting computing into everything. And when I say everything, I really mean everything. Right now, where we don't put computing, it's sort of our imagination is the limit. What this really means is that when, I mean, for example, you all know a bridge fell down in Minnesota several years ago, and they built a new bridge. But, you know, bridges shouldn't fall down. And one of the ways of making sure they don't, other than, you know, build them right to begin with, is monitor how the bridge is doing for vibrations and everything else. This new bridge is full of sensors. So a bridge without sensors will be known as a 20th century bridge. All new bridges will be full of sensors that allows the right experts to monitor it to figure out, is it okay, or are there vibrations, or are there problems that could cause things to happen badly? In the same way, we're instrumenting the electric grids. You've all heard, I'm sure, of smart grids and things like that. We're instrumenting all the equipment in the oil industry, all medical equipment, on and on and on and on. So what is really so interesting here is that whereas computing used to stop at sort of the legacy PCs, it's jumped over and it's become integrated into the physical world all around us. And I view this as almost the golden age of design, because somebody's going to have to design all this new IP-enabled stuff, and if they do a good job, it'll be wonderful, and if they do a bad job, it will be really bad. And I guarantee you, it will take us a while to figure out how to do it well. Then, all that information that is produced by these things will have to be managed very carefully by these gigantic data centers that we were talking about before. And we'll have to be really careful at how well we do that, and we talk about that because the amount of information coming at this, the number of services, I guess I skip one slide. As we have more and more mobile devices, we will be developing more and more applications aimed at those mobile devices. And you have billions of mobile devices, you'll have huge numbers of applications. So you put together this gigantic number of devices, you put together all these sensors, and you can see that you need some very sophisticated data centers, but I think of it as services and information factories kinds of stuff to manage all this. By the way, all stuff we quote unquote know how to do. It's just good engineering applied to these problems, lots of discipline. But perhaps what makes this even more fascinating is that a lot of that information coming from all these sensors is coming to us in real time. Remember, if you're going to do something to help electric grids, You don't want to find out 3 days later that there was something wrong with the electric grid. You want to find out a millisecond later. And the only way you find out a millisecond later is you're constantly monitoring all the information that's going on. If there are traffic jams in Boston and you want to be able to react to it, you don't want to react an hour from now. You want to get the information in real time and figure out what to do. So we are looking at more and more and more applications that are getting information in real time. Now, getting information by itself is not very interesting. What is interesting is how do you analyze that information? How do you extract out of all that information the insights to tell you what the hell is going on? And even better, how do you maybe in real time do some modeling to tell you what the hell do I do now? So if Boston is so blocked because of traffic and you want to figure out how to do it better, you know, that takes a lot of analysis, modeling, simulation. But the good news is we have all these wonderful supercomputers that have nothing better to do than to do analysis, modeling, and simulation in response to whatever you tell them to do. So we have these new capabilities that if we properly put them to use, we can attack problems that were science fiction only a decade ago. That's really what's so exciting in all this stuff. Now, in IBM, we launched an initiative to go after this, which we call Smart Planet, which is making this observation that I've been talking about, that our planet and everything in it are becoming increasingly instrumented, increasingly interconnected, and if you get the right information and analyze it the right way, you can make almost anything out there behave, quote unquote, more intelligently. This is not artificial intelligence at all. This is the kind of intelligence that if you ask me, okay, how do I cross the street and don't get hit? I would say, okay, go to the corner, look right, look left, and if there are no cars coming, cross the street. Now, you would say, that's not intelligent. Okay, then you cross the street without looking and see what happens. And the number of problems and the number of decisions people make in the world that are the equivalent of crossing the street without looking is huge. Some of it because they didn't have the benefit of an Olin education, so they don't know they should think like this. And some of it is because until now, we haven't had the wherewithal to gather the information that tells you what's going on. So it's intelligent based on access to information and its analysis. Now, why is this critical? Well, if you look at the problems we deal with, let alone the problems you all have to deal with, you younger people than those of us with grayer hair, the world is getting much more complicated. And because it's all interconnected and all these kinds of problems, we need to figure out how to manage it better. We need to figure out how to make our use of resources more efficient, our use of water, our use of electricity, our use of energy, our use of just about everything. But another problem is that because of the unpredictable nature of very complex systems, we're going to continue to have more systemic problems. And the only way to deal with these very complicated systemic problems is to keep analyzing what's going on, anticipate the problem, and act on it. How does the Weather Bureau know where a hurricane will hit? Now, hurricane is a very good example of a very unpredictable system. And what the Weather Bureau does is, it sends airplanes into the eye of the storm. What are those airplanes doing? Gathering real-time information. Where does all that information go? Into these massive computers that sort of do their best to predict the path of the storm. But if you say, well, you predicted once, and now for the next 2 days, you know what's happening. No, because these storms have the equivalent of a mind of their own. They're unpredictable. So you predict it to the best of your information. And then 10 minutes later or an hour later, the planes go out. You get more data. You keep doing predictions. And so you see these cones of probability where things are likely to hit. And notice that the farther out in time, the more spread out they are because you really don't know. However, by constantly gathering fresh information and constantly analyzing and modeling, you can do a damn good job. And that's really sort of one of the best examples we have where we've made gigantic progress in predicting something bad. Now, I bet many of us wish our sages running our financial system had done that, but they thought our financial system was like a day in the park, not a hurricane, but something that you don't have to predict. It self-adjusts, the free market takes care of everything, and they just missed it. They just weren't thinking like systems people. They were probably, I don't know what degrees that people got, but they didn't get the right degrees, I think. By the way, I have my PhD from the University of Chicago, which is famous for its Chicago school. So you can imagine my views of Chicago school economists are not totally popular in the University of Chicago. But even in the University of Chicago, the best people have moved on. And they are behavioral economists, which are much more what we need to have. So in IBM's Smart Planet thing, all of a sudden, we can start tracking problems with this approach of instrument interconnect, analyze intelligence, all over the place. Let me take one, smart food systems. You would say, who the hell cares about that? Well, remember, in today's world, you are exporting food all over the place. And every so often, something happens, like mad cow disease or E. coli in some batch of spinach or something. Well, at that point, the ideal thing is to be able to trace where did this come from. If there is mad cow disease, where did this cow come from? What other cows were around in it? If you don't have any information or no ability to get it, you're in trouble. But if from the day the animal is born, you put a tag in its ear, say, that you can track through its life, then when a problem occurs, you can go back and very quickly find out where that animal was born and begin to get a grip on what's going on, start doing some modeling, figure out what other animals came from the same batch, I would say, but the same farm or the same whatever, and trace it all very quickly. And in today's world, the ability to respond quickly to these kinds of problems is really everything. So that's just one example of a new kind of application that's critical to society. I think that if somebody here asks me, sort of what's the most complex and critical application to apply these smart ideas to, I would say, healthcare delivery. Because there's probably no more important problem that needs more attention than healthcare delivery. I don't mean medical research. Medical research gets huge attention by the NIH, and these are people who keep developing new cures, new procedures. But what they forgot, or the HHS, Health, Education, and Welfare, is that in order for those procedures to be applied to humans, you need a healthcare delivery system, and you need a payer system. And those two are, to say it in a kind way, a mess that we're trying to fix. What do I mean by a mess? What do we mean by a mess in engineering? Well, we mean the costs are huge, the quality is low, nobody knows what's happening. Is that a fair definition of a systems mess? And boy, do we have that. But we also have all kinds of new tools and new capabilities to begin to put our arms around this super complex system and begin to make progress. So it's one of the more interesting things we need to do. Another fascinating but incredibly complex set of problems are problems in urban environments, traffic management. It's a problem that's going to keep getting worse and worse and worse. I don't think I need to tell anybody here. And there are all kinds of new ideas, like congestion management that's been implemented in London and Stockholm and Singapore and other places that US cities badly need, but for political reasons, we don't have. Well, in my mind, when political leaders have no information, then a problem is a political reason. If, for example, we don't have a lot of debate whether if you want to put up a tall building in Boston, you should do it with the best civil engineering practices. We don't have enough debate because over the last, 50 years or longer, everybody has agreed that if you want the building to stay up and not fall down on people, these are the things you need to do. Remember, before that, they could argue, well, you're trying to screw me by making me use steel of a certain kind, or these fire codes are not right. Then you would have political debate. Once we began to understand the problem better, analyze, model, etc., we took it out of the hands of, quote unquote, just the politicians, and we were able to deliver to them good data, good models, good principles. I mean, we may still have politicians that say, well, I don't believe in math, and I'm sure we have some like that. I don't know what to do about them, but most are not like that. So the more we take these problems and transform them from ideological problems into systems problems, engineering problems, the more progress we can make, especially as time goes on and people just get used to, well, it's stupid not to use the best models with the best information, or maybe you don't get elected if you use those kinds of things. Law enforcement is another fascinating example. IBM worked with the city of New York to develop what's called the RealTime Control Center. It's in one police plaza near City Hall in Manhattan. And if you look at that command and control center, it looks like something out of a science fiction movie, because you enter this huge room with this gigantic screen, and in the gigantic screen, every time there was a call that they are responding to, it shows up there. So the screen is a geographical, it's a map, but it has precisely who is responding to what. And then there is a group of expert detectives with terminals there, and they are assisting the officers who are responding. So somebody says, go to this building. Now, doesn't it make sense if you're going to go to that building to know who lives there? What's their history? Have we had other problems? How about in the vicinity? Now, the officer, the man or woman responding to that, they are rushing to respond. They cannot do that. But a detective at the terminal is analyzing all that as they rush, and they are feeding back the information. And all of a sudden, that detective, that policeman or woman, is able to do a far more effective job, be much safer, and quote unquote, all we have added to them is real-time information. And this is an example of a system that's viewed as a huge success in helping New York City significantly reduce crime. I don't know if you know, New York is about the safest large city in the world right now, pretty much up there. And it's because they have applied this kind of very disciplined approaches to fighting crime and things like that. Healthcare, we talked about, lots and lots of work here. Energy, I don't think I need to tell you in Olin College how important it is to be efficient in our use of energy. And by the way, I know there's a lot of discussion about whether the planet is getting warmer or not. Forget that for a second. If you are a really good designer, wouldn't it be terrible to waste energy? I mean, that's just inelegant design. I don't know how you can be a good engineer, regardless of whether the planet is getting warmer or not, or whether we do that. It's a no-brainer to design. For example, there are all kinds of ideas for commercial buildings to be incredibly more efficient in the use of energy, instrument them so that, you know, if the sun is hitting a glass wall, the glass wall turns dark so that the sun, you know, doesn't penetrate. In the summer and in the winter, it opens up, saying, come right in, because you need the heat. You don't need to worry about anything else. It's just sound engineering. You'll lower the cost of running the building. You'll do everything. And if the Earth is, in fact, getting warmer because of CO2, boy, that's wonderful to be able to anticipate and do all kinds of things. So energy, there are lots and lots of things going on. One of the most important areas where we have been focusing all these smart planet ideas is in cities. And in fact, we just had a really great conference in New York City, October 1 and 2, on the whole theme of smart cities. Why is this such a big deal? Well, in 1910 or so, about 12–13% of the population of the world was in urban areas, and the rest was in small towns and agricultural areas. Now, about 50% of the population of the world, roughly 6.5 billion, live in urban areas. By 2050, UN population studies predict that over 70% of the world's population will live in urban areas. The population is supposed to grow from 6.5 to over 9 billion. All of the growth will happen in urban areas. If we don't do something to better understand how to deal with big, complex urban areas, but we are in trouble. If we attack this, And if you are, again, an engineer, a systems person, an Olin graduate, this is like the candy store of fascinating problems, because you just get to think about all these incredible problems. And remember, you don't just think and write papers. You can do that also. You get to design, and you get to test, and you get to model, and you get to build, and you get to do all kinds of things. Now, the best framing of urban systems I've seen comes from colleagues I work with at Imperial College. Actually, it's a project called Design London, which is, this is very telling. It's three institutions together: the engineering part of Imperial College, the School of Management, and the Royal College of Arts, the RCA, which is probably the world's most famous school of design. When you say that, and if it's not the most famous, it's right up there. This is very telling, because Design London, you know, we're designing systems. So it's not just doing fast Fourier transforms or whatever. You can do that too, but it's what are we designing, and then what are we building. And you can look at this in three main areas. One of them is all the systems that have to do physical infrastructure. That is, a good city needs good traffic, good parking, good transportation, good energy management, security, surveillance. So all these have to be done. But then, remember, cities are full of people, right? And people need jobs. And so a good city spends a lot of time thinking about job creation and making it easy to start new companies. How about taxation? What's the relationship between taxation, job creation, entrepreneurialism, and so on? And these two are very connected, because if you have jobs, and if people have to get to jobs, you need transportation system. If you have a bad transportation system, guess what happens? People can get to jobs, so you have a problem. So you can't look at these things in isolation. You have to learn how to do these things in a more holistic way. But it's not enough to have jobs. It's not enough to have good transportation. People need more than that. Like, they need to be happy. They need a good quality of life. And what do we mean by that? Well, they need good education. Otherwise, they won't want to live there or raise families for sure, because their children need that. How about health care? Can you be a good city with a lousy healthcare system? I don't think so. How about entertainment? You can say, well, that's just entertainment. Well, but if you don't have entertainment, you don't attract young people. And if you don't attract young people, you have a problem. I don't think I need to convince you here. And notice that the cities that we consider the most dynamic, cities like Boston, New York, London, Berlin, you walk the streets and boy, they're full of people like you. And when we think of a city with no young people, we tend to associate that with, I don't know, either a retirement community or, sadly, a lot of old industrial cities are in that category. All the young people left, and those are dying cities. And then something very important, when you have a system of systems, you need to optimize it around some objective. And I think that for a city, the objective has to be something like quality of life or livability. And if you said, well, what the hell do I mean by that? Well, again, that's what we need to study. So if you want a city to attract people and you get the best information possible, what are the things that cause people to want to stay, move in, raise families, get jobs, and that's what you want to optimize. Something like quality of life or livability. So these problems are so incredibly fascinating because, first of all, I hope you get the sense from me, I view this as engineering problems, systems problems, technology problems, mathematically oriented problems, science problems, but they are very much market-facing problems. We're trying to do incredible things for society and for the organizations and institutions of society. So let me just finish by asking some rhetorical questions. So what kind of people do we need to tackle this kind of near impossible problems? And a term that we often use is that for this problem, we need T-shaped people. And that is people who are very good at something, very deep in something, but very broad in addition to that. So, because what you really want, since we need to bring them together in team, the team has to be composed of the right sort of depth of different people, but what keeps the team together, what makes them work together, is their ability to communicate, to be broad, to have a common language, because there is no way you can ever tackle these problems just with a set of isolated people. You just cannot do that. It's impossible. It's not even worth trying. And it probably sounds like something from your slides. What we need more than anything is people with the right technical skills, because these are god-awfully complex problems, the right market skills, because you need to understand the financial implications, the economic implications of all this, but then the people skills. Because remember, at the center of all these problems, I mean, you cannot do a good healthcare system that ignores patients, doctors, and nurses. You can do that. I mean, you can try, and we probably have done that in the US, but then you'll have a bad system. You cannot ignore the people in the system, and so you need people who are very good technically, very good business, but who have a good understanding of how to deal with people, how to communicate, how to learn, and how to listen, a quality that until Olin and recently, we always said, well, we don't need engineers to do that. I don't know who we thought would do that for us, but I don't know why we thought that, but maybe that's a whole other story. And what is really happening is very much what we need is what you're all doing, which is move from the classic world of science and engineering, and that will remain. You know, we always need legacy disciplines, so those will remain. But I really think where the world needs to really go is these multidisciplinary approaches to these fascinating and critical problems of society. Thank you.